Hello everyone, I am Emery, your host for today. Welcome to Say to Me and I'll Listen to You. Today, our guest is a well-known scientist from Pat Science Laboratory. Let's now welcome Dr. Infante together with his students, two aspiring scientists who are also studying in Pat's College of Aeronautics.
Hello, listeners, and thank you, Emery, for inviting me to this podcast.
Good morning to you, Dr. Infante. For today, what are you going to share with us and especially with our listeners?
Does anyone know anything about the rate of reaction or chemical equilibrium?
Hmm, I remember from my senior high school or college year, the topics that you mentioned were discussed, but I don't really remember that much. Can you please tell me about it?
Okay, first, what is rate of reaction? The reaction rate or rate of reaction is the spread, the speed at which chemical reaction takes place, defined as proportional to the increase of the concentration of product per unit time and the decrease in the concentration of reactant per unit time. Reaction rate can be very dramatical. In chemical reaction, chemical equilibrium is a state in which both reactants and products are present in concentration, which have no further tendency to change with time. Usually, this state results when the forward reaction proceeds at the same rate as the reverse reaction. For example, when we add up hydrogen gas and iodine gas, we can form a hydrogen iodide, and if we break down the hydrogen iodide, we can also get the hydrogen gas and iodine gas.
From what I heard, I remember how I struggled from this subject. Can you tell us what are the purpose of studying the rate of reaction or chemical equilibrium is?
Of course, rate of reaction is simply a measurement of chemical activity of a certain reaction, just like any other types of measurement, such as length, mass, and time. Reaction Rate of reaction is playing a major role in our daily life. It is crucial to optimize the rate of reaction to obtain the best performance of the reaction. And why is studying chemical equilibrium important? Because equilibrium plays a very important role in the study of chemical reaction, as it tells us about the direction of chemical reaction.
From what Dr. Infante said, we can say that he is a really one of the best scientists in our country. For that, we want to thank you for the information you have given to us. Now that I know you have an idea on what our topic is for today's podcast, let us know let us now welcome our two aspiring scientists, starting from Nicole Malabanan.
Hello everyone, Mr. Emmy.
Hello Nicole. Is this your first time to be part of a live podcast?
Yes, and I'm a little bit nervous.
Really? I think you are as good as Dr. Infante. I believe that a good teacher makes a good student. From the introduction of Dr. Infante, what are the topics you're going to discuss today?
So I'm going to discuss what I know about chemical equilibrium.
So let's hear from Nicole.
So let me discuss first chemical equilibrium and its concept. Chemical equilibrium describes the state of a reversible reaction in which the forward and backward reactions happen at equal rates. In this state, the concentration of reactants and products are stable and do not change over time. Since the equilibrium depicts the state of reversible reaction, in reversible reaction, reactants A plus B are constant converted into products C plus B, and vice versa. This means that the forward and backward reaction take place at the same time. The reversibility of a reaction is depicted by double arrows in a chemical equation. A plus B goes to C plus B. In the equation, there's only A and B, so only the forward reaction is possible. When C and B build up, the reverse reaction will speed up. while the forward reaction slows down. Eventually, when the rates are equal, the concentration of the reactants and products no longer change with time.
Moving on to our second inspiring scientist, let us welcome Leah Luartes.
Hi everyone. Thank you very much for having me today. I will be discussing an overview about equilibrium constant and Le Chatelier's principle. The equilibrium constant, represented by Kc, is a measure of the composition of a reaction at equilibrium. Its value is equal to the reaction quotient in a reaction at equilibrium. As you can see on the screen, the equilibrium constant is calculated by dividing the concentration or thermodynamic activities of products by the concentration of reactants. The concentration of each species is raised to the power of that species coefficient in the balanced chemical equation. On to the next topic, the Chatelier's principle. This principle states that if an equilibrium is disturbed by changing the conditions, the equilibrium moves to the left or right, left being the reactant side and right the product, to counteract this change. Thus, a new equilibrium is established under different conditions. Changing or manipulating the temperature, pressure, and concentration will affect the equilibrium. To start with, the effect of temperature. Exothermic reactions release energy. Therefore, in this case, heat is considered a product. If we add more heat to the system, the equilibrium will shift to the reactant side to counteract the increase in product. In endothermic reactions, heat is considered a reactant because the reaction consumes energy. Thus, increasing the temperature will shift the equilibrium to the right. The next one is the effect of pressure. If we increase the pressure, the equilibrium will move in order to reduce the pressure again. This is achieved by lowering the number of molecules in the system. Hence, if we increase the pressure, the equilibrium will shift to the side, where the number of moles is lower. And lastly, the effect of concentration. If we increase the concentration of molecules on one side of the reaction equation, the equilibrium will shift to the opposite side. For example, if we increase the concentration of reactant, the equilibrium will shift to the product side.
We can say how good these students are and how confident they are discussing the topic.
So let us now talk about the reaction quotient. The reaction quotient Q can be used to predict the directionality of a chemical reaction when compared to the equilibrium constant Kc. So where the equation A plus B goes to C plus D, which is A plus B is the reactant and C plus D is the product. The formula will be Q equals product over the reactant. If reactant quotient is greater than equilibrium constant, the reaction forms reactants, and if the reaction quotient is less than equilibrium constant, the reaction forms product. And then if reaction quotient is equal to equilibrium constant, it can be equilibrium. It is calculated similarly to Kc, however, the concentration of products and reactants are taken at any point in time while the reaction is not in the equilibrium.
Let's not now talk about catalysts. Catalysts offer an alternative route for a reaction with a lower activation energy, thereby making the reaction proceed at a higher rate. Catalysts do not change the equilibrium of a reaction, they can only increase the rate. Without a catalyst, the reaction would therefore still proceed in the same direction, only slower. In this figure, it is shown that a reaction from a substrate to a product is a transition from one energy state to another. A transition state exists between the substrate and the product. This state has a higher energy level than both the substrate and product. A catalyst will lower this energy level so that the transition energy is switched more easily, and this results in a faster reaction.
Wow, these two must really know their chemistry. I'm not an aspiring chemist or a doctor myself, but I assure did learn from them. What can you say about these students, Dr. Infante?
Honestly speaking, I am surprised by how much they know about chemical equilibrium, considering that they are still studying. Okay, now that we all know the concept of the rate of change and chemical equilibrium, let me explain how to solve the final concentrations at equilibrium. Okay, here's the problem. Calculate the three equilibrium concentration when Kc is equals to 0.068 molar with an initial concentration of CO is equals to zero point 0.5 and Cl2 is equals to 1 molar. So, the first thing that we need to do when we are solving these kinds of problem is to analyze the problem carefully. In order to solve this problem, we are going to use algebra and create a ICE or ICE table, which stands for Initial, Change, and Equilibrium. So let us answer the table now. In in the case of particular problem, we're going to put 0. In cobalt chloride, we will just put zero point 0.5 because that's the given, and as well as the chlorine gas, which is 1.00 molarity. In answering the change, we will just put negative x because we see a 1:1 stoichiometric reacting ratio. The COCl2 will increase by that amount, so we will just put in the x. The third column, we will simplify the initial and the change, making it zero point 0.5 minus x and 1 minus x. And the COCl2 will remain x. Okay, so now we completed the table. Now we will now we are done with the table. We'll solve our equilibrium expression. Our equilibrium example is nothing more than the ratio of our reactant raised to their coefficients and product over the top of that. In our case, our expression will look like this. COCl2 is CO times Cl2 divided by COCl2. If we simplify this, we are going to have 0.068. We need to use quadratic equation to solve for x. The value that we got for x is 200, 0.260. Then, we need to substitute 0.260 for the x that we put in a while ago. As for the COCl2, well, there wasn't any of it initially, so we will just going to put 0.260. For CO, it will become 0.5 minus 0.6260. Then, if we simplify it, the equilibrium concentration will be 0.240 molarity. And finally, for Cl2, it will become 1 minus 0.260, and when we simplify it, the equilibrium concentration will be 0.740 molarity. So, so that it is an example showing you how to use the equilibrium expression and the and initial concentration to find the final concentration at equilibrium.
Wow, I thought I was listening to Albert Einstein. They were really good, Dr. Infante. I think you're good to retire early because your laboratory will be in good hands. And thank you everyone for listening to this podcast. I'm hoping that you learned something today. This is your host Emery. Say to me and I'll listen to you.